A very pleasant and calm morning to one and all present over here. I welcome you all to the day 4 of the short-term course STEM 2023. Today's session will be taken by Professor Waypala from University of Moratuwa, Sri Lanka on the title Optimized Operation of a Solar Battery, Diesel Engine and Grid Connected Microgrid with Energy Cells to the Utility. A case study for the microgrid at Sumanadasa Building, University of Moratuwa, Sri Lanka. Professor Vijaypala is an electrical engineer graduated from University of Moratuwa, Sri Lanka in 1991. He served in the private sector electrical engineering industry for 15 years before joining as a senior lecturer at the Department of Electrical Engineering of University of Moratuwa in 2006. He obtained his Master of Engineering degree in the year 2001 from University of Moratuwa. He has been a chartered electrical engineer since 1996 and he is a fellow of the Institute of Engineers, Sri Lanka and an international professional engineer. He has been chairman of Sri Lanka Electricity Board National Engineering Research and Development Center of Sri Lanka and LTL Holding Private Limited. On substantial leave from the university, he served as CEO of Windforce Private Limited, the largest renewable energy company in Sri Lanka from February 2018 to February 2020. He is a board member of the Smart Energy Council Sri Lanka. Currently, he is serving as a professor and the head of the Department of Electrical Engineering, University of Moratuwa, Sri Lanka. Now I welcome Professor Vijaypala to deliver his lecture. And this is over to you, sir.
Okay. Good morning. Thank you very much for the introduction. And I take this opportunity to thank the organizing committee and Professor Moratuwa for inviting me to deliver this speech this morning. And a very good morning to all of you once again. And let me share my screen. I hope it will be working. Can you see my screen? Or? Professor Moratuwa, can you see? Are you able to
yes,
see?
Yes, sir. Your screen is visible. You just make it full screen, sir.
Okay. Hope now everything is okay. So when Professor Moratuwa suggested this speech, and we were looking for a talk and for a title, and then looking at the theme of your sustainable theme of your STEM 23, I suggested this title to introduce to you, this learned crowd, the recently implemented microgrid at our university in Sri Lanka, and which was, of course, funded by Asian Development Bank and implemented by one of the electricity distribution utilities in Sri Lanka, Lanka Electricity Company, Private Limited. And it was implemented during the last couple of years and was inaugurated in August 2022. So it's all about 1 year old now. And so it is in two parts. One is the microgrid. Second part is the laboratory attached to the microgrid and the associated equipment. So I will first go through the microgrid, and then we will proceed to the look at what are the facilities available in the lab. I hope this will be useful to you because these are new concepts coming up. So one day you might already have some of these things in your part of the world, and maybe someday you might need to implement similar thing. So by learning from what we have done, you will be able to do them better and to be in a more optimistic optimum way. So with that, let me proceed with my presentation. And I thought of including one slide about my university where I learned and now I'm teaching. And by the time I was in this university in 1980s, it was only 2 faculties, engineering and architecture. And now we are 6 faculties in addition to engineering and architecture. We have an IT faculty, a business faculty, a medicine faculty, and a graduate studies faculty. So there are 6 faculties at our university. And we are about 20 kilometers south of Colombo. And this is the area that we are occupying. And you can see we are bordering a river, Bolgoda Lake. And then we are a bit congested. In our opinion, it is too many buildings in this because we can't expand land-wise because it's a very congested area. You can see all around us, it is a lot of congestion and no bare lands are available to acquire and so on. So, but we are happy here, so can see. And so in this microgrid project, we have used 3 building blocks in implementing this. One is the Sumanadasa building, main component of it. And right now I am also sitting in the ground floor of this building. And then there are 2 canteen blocks next to us and the new administration building where the Vice Chancellor and his office is located. And all these are connected to this microgrid. And you can see here, that is the incoming distribution line from Lanka Electricity Company into our premises. And then it is going to various buildings. Of course, there are several lines coming in. This is the line connected to our buildings. And then you can see now, as implemented in this project, we have installed the battery storage and the diesel engine at the same location. So diesel engine, battery storage, and the incoming transformer from the 11 kV distribution system is located here. And the microgrid is spread in these 3 building blocks. Sumanadasa building, 2 canteen blocks, and the administration building. I will take you through these things later. Just to give an idea, you can see our playground and other buildings and other faculties all are spread out in this about 20-acre land area. And I will not go through this slide, just included for the academic information. So we are moving away from conventional grids now to smart grids due to a variety of reasons, especially under transient conditions when there are problems in the big network. You can isolate yourself to microgrids or smart grid components, and then self-sustain until the problems are sorted out in the main grid. Or else you can have your own microgrid connecting several hotels, academic institutions, etc. So that for economic advantages, like you don't have to pay for the demand charge, etc. Only the unit cost will be there. So now with the lowering of the battery cost, solar PV cost, etc. So the economic sense is coming into microgrids, which were and also today also little on the high expensive side, but the prices are coming down. So in the future, they will be more and more feasible. So this is the basic architecture of this project. And we can see that I told you that at the entry point of the transmission line, you can see here, there are 3 devices. One is the utility grid, incoming grid, which is connected to a 630 kVA transformer. And then at the same place, we have installed the diesel generator, 600 or 660 kilo kVA generator, and the battery storage, 460 or really about 418 kilowatt hour and 418 kilowatt. So it can discharge in 1 hour, full capacity. Battery storage also, and the associated inverters and other things with the step-up transformer as well, dry type transformer at the entrance location where the transmission line enters. So all these things are there. Then the microgrid parts comes here. You can see 3 buildings that I described. Main building, Sumanadasa building, where I'm just now. So there are a large number of solar panels on this building's roof connected to the grid, go to our system bus bar, AC bus bar through 3 inverters. And there are 2 canteen blocks next to us, which have also 2 canteen blocks. They have on their roofs some solar panels and 2 inverters to the 2 blocks. And then in the main administration building also, there are solar panels, PV panels, and connected to 3 inverters. So there are altogether 8 inverters connecting the solar PV to the low voltage bus here. And we can see the controllers, main controller, and 3 controllers here. I will go through some of these architectures and designs in a little while. And these are the single line diagram of these connections. You can see 3 building blocks. You can see main building is here. Sumanadasa building, 200 kilowatts of solar PV are housed in the roof of this building. And in the canteen blocks, 50 kilowatts, smaller unit. And in the main administration building, another 100 kilowatts. So it's about roughly about 350 kilowatts of solar PV roof mounted. And the diesel generator and the battery bank. So this is the single line diagram, and the incoming grid is here. And we bought 400 peak watts modules. And so these are the performance characteristics, which I don't want to go through. I'm sure all of you are very familiar with these things. And these are the inverters, MR inverters. And there are 8 of them connecting at different locations, connecting the solar PV to the network. And when we wanted to implement this project, this is a ADB fund, so they went for competitive bidding, and so we qualified a company in Germany to implement this project called D-Hybrid. So they have what we call this universal power platform, and they have implemented many similar projects elsewhere. So we looked at the references and agreed to let the project be implemented by them. So it was implemented by them through a local company called DMO, Diesel and Motor Engineering, who did the real installation under the supervision of this D-Hybrid, a German company. And this is the system overview, which we looked at earlier also. There's the main controller, and then the 3 subcontrollers, looking at the 3 buildings, and then all are integrated by the main controller, which is controlling the supply sides, other supply sides, and diesel generator, grid, and the battery. And now we will look at the subsystems in a little more detail. And the main controller part you can see, so it is controlling the grid and the diesel generator and the battery storage, and all the control topologies and the architecture is given to this controller program. And so we can, of course, for the optimization, we can change the operating points. For example, when the battery should stop discharging, for example, whether it is 20% SOC or whether it is 30%, etc., looking at the battery health, etc., and looking at the current literature on the lithium-ion batteries, we can change them for the longer life on one hand. On the other hand, getting the maximum use of energy storage to meet our demand when and where required. And so this is the main controller part. And you can see there are 3 control levels in this microgrid: primary control, secondary control, and tertiary control. Under primary control, we regulate main relays, circuit breakers, and the voltage and currents at different locations. And you can see that these are the control devices that that are controlled by the primary control, what are marked in blue color. And so that has the priority. And then comes the secondary control and the demand response, VF regulation, synchronization of the generators to the system. The SCADA and other communication protocols all are controlled by the secondary level. And these are the secondary controls mainly we are using. And tertiary controls, energy trading, because we have, I will go through that in the last few slides. In Sri Lanka and like elsewhere in the world, we have this rooftop energy sales option. So we have a business model also where the excess energy at any given time, if our solar generation is more than the demand, we sell to the network. And there are 3 schemes available in Sri Lanka, which I will describe in the latter part of my delivery. And so we get an income, and we are trying to get that income and keep it in a fund so that we can use it for future development as well as maintenance of this system. So energy trading is part of this microgrid, and then the load management, optimization, forecast, and dispatch. So this is a photo of the master controller mounted on a panel. And these are the the controlled parameters by the main controller. And you can see, I will not read everything. And the PV interface, battery system, battery inverter, diesel generator, direct load control, power meters. And we have a meteor station also here, where it can measure the wind speed and the temperatures and the irradiance and the humidity and other parameters, and which are also input to the main controller. And then the breakers, the status of the breakers, several breakers that we have. Then the main controller will give its commands to different devices as to how they should operate. For example, it will give a signal to the battery system saying whether it should be charging or discharging. Because when we have excess solar generation, we charge the batteries so that we can use it at later when the solar PV is not available in the evening. We will look at some of the charging and discharging characteristics while other devices are operating in some other slides. And these are these various SCADA screens that are available for us to observe the system. And there are a large number of parameters which we can see and then look at. And then if there are any troubles, we can troubleshoot them. And if any part of the solar PV systems are not working or their inverters are having issues, all the operator can see from these SCADA screens, which is also housed in the microgrid laboratory as part of it, so that they can, on one hand, do the experiments, and on the other hand, see the real microgrids, operating parameters, and look at the trends and battery charging, discharging characteristics, all, and get the first-hand information as to how these things are operating. And then this is the battery system, 418 kilowatt hour, 418 kilowatt. That is, it can discharge the full charge in 1 hour. And but of course, we are not reducing that fast because our requirement is slowly changing. So we will let the battery discharge over few hours when we have, especially during the evening, when it is fully charged during the daytime solar input, and then later when the evening peak comes, demand comes with the lights and other things getting on, we are usually using the battery storage rather than importing energy. And this is a look at the battery racks, Samsung lithium-ion battery racks. You can see all of them are housed in a air-conditioned container. We will have a look at the container housing, and you can see the battery inverter, which is also housed in the same container, which are located near the grid interconnection point. And you can see the battery system can operate in very flexibly, and you can see it can in the first quadrant or second, third, fourth, as we require. So depending upon the the, the, the load requirements or charging requirement, we will program. The master controller will give directions for the battery systems to operate. But of course, we are using the present day knowledge on the health of the lithium-ion batteries so that we can use them 10 to 12 years at least with good state of health. And therefore, this battery operation should be carefully planned with our battery management system. And of course, we have the flexibility of changing, for example, the depth of discharge, which we are doing in consultation with the battery manufacturers and the present day knowledge, so that we will not unnecessarily sacrifice the. I hope my voice is clear to you, Professor Monalisa. Or anyone can give me some feedback.
Yes, sir. It's clear, sir.
Okay, thank you.
Yes, sir.
Thank you. Okay, so that you can see the batteries can operate in a wide range of operating points, and it is for the flexibility of our meeting the demand and also looking at the health of the batteries. So this is the battery, how the batteries are connected. You can see there are 3-level inverter, and then the DC distribution, and so that we get the necessary. Our system is 400-volt 3-phase, so we produce 400-volt 3-phase using this architecture, and then the batteries will be connected to the low voltage grid. And this is the container housing where the batteries are housed. You can see the battery racks and the 5 battery racks and the UPS for this, and then the transformer for the connection. And all are housed in air conditioned container. So here's a look at it, and you can see the battery racks here, and the transformer and other devices. You can see this is where this is our transformer, and then the incoming lines and outgoing lines as well. Incoming lines is here, cable, and then the container housing this is the diesel generator, and the next to it is the the one is the diesel generator, and the next to it is the battery container. So there are 2 containers here really. One is for the diesel generator and one is for the battery rack. And this is the diesel generator, and it is also directly connected, and we try to minimize the use of diesel generator and to try to manage with the grid as well as the battery. And if there is a grid failure, announced grid failure, we will still try to optimize the battery and use it and minimize the diesel generator option because it's the most expensive option for us. But of course, there are scheduled maintenance from the grid operator, LICO, and then in that case, we will have to use the diesel generator to support the system until the grid power is restored. And so this is our low voltage bus and how it is connected to various loads, main distribution board. And we can see that all the buildings are connected to this bus, the main distribution board. To all the 3 buildings get power from it. And we can see a look at the main distribution board. And then this is the canteen block and the Sumanadasa building area, which are close by to each other. And so we can see that they are controlled by 2 separate controllers. And then the metro station is also connected to this because it's housed on this, the roof of one of these buildings. And we can see that it gives various measurements to the main controller through the subordinate controller controlling them. And this is the solar PV panels, and you can see they are mono PERC half cut cells, and with the 400 peak wattage, and so that was also selected through a competitive bidding process, and we thought they are the best at that time. And so all the panels are with that make. So this is these are the PV inverters. So this set is Huawei type, and so they are connected to the different buildings, and 3 of them are in the Sumanadasa building, and 3 of them are in main administration building, and 1 each at canteen blocks. And so this is, as I showed you earlier, this is the one grid with PV and battery energy storage all working together, and without the diesel engine. This is normal operation, and of course the battery operation, whether the battery is connected, whether the battery is in charging mode or discharging mode will be decided by the demand, supply demand gap, and also to minimize the imports. So here we are importing energy from the grid and using our own energy generated by, if it is daytime, from the solar panels, and of course in the evening, for we have 416 kilowatt hours stored in the usable energy stored in the battery system. Then how it can be used to minimize the imports? That is our criteria. And here is one day on grid with PV and battery energy storage system, how it has operated. You can see it depends upon the whether it is a working day or weekend, etc. Because the load varies a lot. We can see the load is this. Can call it gray line. Here you can see the load variation, right? You can see it on this day it has gone only to 150 approximately kilowatts. So it may be a quite a light load. I have seen it going up to 300 kilowatts and so on some days. So it's a lightly loaded day. You can see the solar generation coming and peaking to about, we have 350 kilowatts. So due to various derating factors, we get on this day we have got about 200 and I would say 50-60 kilowatts peak, and then going down. It says has been a smooth day, and then we can see how the green color one, you can see the battery operation. So you can see the battery has been charged during the early morning hours, right? And then you can see the blue one, and the excess energy has been sold to the grid as well. Battery, after charging the battery, the balance has been, you can see, sold to the grid. And above the zero line blue color one are the imports, and you can see we have fed back to the grid as well, which we can deduct from our imports later. And then you can see at the night time we have after 6 p.m. about 6 p.m. we have discharged the batteries gradually to minimize the imports. You can see, if not for this green color battery discharge energy, and then we would have to import the entire thing. And mind you, we are on a time of day tariff, so that when we discharge from 6:30 p.m. to 10:30 p.m., our bills get quite low. That is why we are not discharging here during the daytime. Daytime electricity imports are cheaper, but we are importing we are exporting during the time where we have to pay higher tariffs because we are charged a time of use tariff. And then we can see the SOC levels here down. You can see we have discharged the batteries up to 20% here on this particular day. You can see. And then is a charging at, you can see the charging here, 200% during the morning hours until about 11 a.m. By 11 a.m. we have charged it fully and then kept it charged and start discharging at about 6 p.m. rather than immediately. So we have used the little bit of grid and solar PV mainly for our demand to meeting the demand that day. And also we have exported to grid the excess, whatever the excess we have. So our battery is charged first, that is first priority, and then the excess is sold, and then we minimize the imports during expensive hours by discharging the batteries in the what we call the peak demand period where the electricity is more expensive. Then this is a case where the grid is not available, off-grid with PV and battery energy storage. And you can see the diesel generator may be in operation or may not be in operation, depending again on the battery's SOC level and also the demand. If the demand can be met by the batteries, we will use the batteries first because these interruptions from the grid interruptions can be short-term. If it's a failure, usually it is short-term, maybe they will correct it within some tens of minutes or maybe half an hour, 1 hour. But there are planned outages, long outages for maintenance, which might extend to 6-8 hours, in which case we will need the diesel generator to come on, especially when the solar PV is not available. But luckily, we have a chance that normally the utilities plan their maintenance during the daytime. So it is about, say, they might start at 9 a.m. and then finish it about, say, 4 p.m., 5 p.m. But during that time, if we are lucky, it's a sunny day, our solar PV is good enough to meet the demand if we are lucky. But we are not always that lucky. You can see on this load day, you can see the load has been quite big, maybe a day where all the lecture halls are working and the peak working day. You can see it has gone to 400 kilowatts or a little more demand. Whereas on this day, the solar generation has been the same like 250, 300 kilowatts, 250 or so. You can see in that case, we have not exported anything on this day, but because our demand can be, we have not put it to the battery also much until the grid. You can see earlier, our demand has started to increase after, say, 7 a.m. That because the university, the incoming people as usual comes around there 7:38, and then the demand has sharply increased. But until then, we have not. Can see the battery has also discharged whatever it has, and then battery discharging has been done only a little bit, and so on this stage, battery charging has not been that successful from the solar because the demand is so high. So it is better to consume there and then because battery also has an efficiency, maybe 85, 90. Therefore, there's no sense in charging the battery and discharging later. So unfortunately, on this day, we have fully used the solar there. And also the battery charging has been done during the night time. So you can see that, and you can see how the battery state of health also has changed. So these are the things the people are experimenting and then trying to see. But you can see now on this days, we could do better if battery charging is done a little also later than our peak payment period. So these are the things that we are adjusting in our system still for our optimizations. So these are some operational comparisons on grid and off grid. And so in the on grid, utility grid works as the master. So it fully controls the frequency and the P and Q. And the battery inverter is set to certain P and the Q and the discharge rate. And the PV set points. And diesel generator we don't use when the grid is available. And the off-grid mode, then utility grid is not available. And then the battery inverter will decide the V and the group and the Q and P. And the PV inverters, if sunny time, will also generate at that time. And the diesel generator will be called if necessary. And that will be decided by the criteria given to the main controller. And then I will little focus on our laboratory, which is associated with the microgrid. You can see this is a photo taken from the entrance side to the laboratory. And of course, on this side, there is a discussion room here for the people to sit down and discuss. And here you can see this is the main controller board where they can see the actual microgrids operating parameters, the SCADA screens. So they can always study how the things are happening in the main microgrid, and their battery level, battery SOC, discharging rates, and at that given time, what are the production of solar PVs in different locations. For example, Canteen Block 1, solar PV, how much is it contributing, and how much is the rated value, and then the irradiance they can see from the meteor station, how much is coming in, and then we can see if they are fouled and can see need cleaning. We can judge from this and how much is the derating that is occurring due to dust and dirt and other things. So we will time to time check the efficiency of conversion, or how much is derated by these factors, and then decide that a cleaning cycle should start sooner or later, because we are in a wet zone. So we receive plenty of rain, and so our panels get auto washed as well. But during the dry wet spells, we have to wash them because there are this area is quite congested, so a lot of dust generation is there. And we can see, I will go through individually each equipment here. You can see there are various inverters and power supplies here mounted, and they are programmable inverters. And then various loads, inductive, capacitive, resistive, electronic loads, and then various other things that are required for the testing of inverters and other things which we receive from industry. For example, when new inverters are introduced to Sri Lanka, normally they are sent to our labs, where we will test them and issue a certificate and saying whether they comply with the requirements of Sri Lanka SLS, Sri Lanka standards, stipulations. For example, how much is the total harmonic distortion that is taking place, because normally they have to be less than 5%. So in this lab, we, in addition to do experiments, we do test the industry components like inverters and certify them whether they comply with the requirements of Ceylon Electricity Board and Lanka Electricity Company, which both will depend upon IEC as well as Sri Lanka standards. Normally, Sri Lanka standards are one-to-one complying with the IEC standards. And this is the laboratory. This is not the microgrid. And microgrid part that I described earlier, this is separate. And this also has smaller solar PV stations, again housed in the same building roof, Sumanadasa building roof. You can see there's one 4 kilowatt solar PV and 5 kilowatt solar PV and a small battery storage. And you can see these are for the students to experiment with. So they can connect them to inverters and various other loads and other things, and then do various emulations, simulations, and we have a grid simulator as well. And using these things, our research students as well as undergraduate, there are set practicals for the undergraduates, and there are several tens of master's students who are also utilizing these things and uh, doing their research on various aspects on battery management systems and various other things together with their various AI and other applications and how to actually simulate, because otherwise you will be doing only with the simulation software simulations, but now they can do hardware simulations as well. And then in addition to that, they can confirm, validate their software simulations through the actual hardware and make their research more rich. And these are some of the equipments that we have installed at our laboratory. For example, this is the 4-quadrant grid simulator. You can see some of the parameters of this grid simulator, and which is we can simulate many versions of the grid, and grid maybe whatever the phase failures and other things, and then see how our systems are working, whatever the experiment they want to check. And then they have multifunctional DC electronic loads and AC electronic loads as well for to be used with their experiments. And then single and three-phase resistive loads, they can adjust them to whatever the values they want. And then they have the cooling devices so that they will not get the heat can be dumped, and so they will act as whatever the loads they want for testing of equipment, whatever the equipment, or simulating their circuits, whatever the way they want, together with the PV as well as with the inverters, and the loads can be made. Similarly, we have single and three-phase inductive loads, and they again can be, controlled, and so that you can set it to whatever the circuit configuration you want to have, of course, within the limits that they are capable of operating. And so we have a transmission line model which can simulate transmission line, like for example, 136 kilometer, up to 77 kV, 100 ampere, 13 megawatt kind of line we can simulate. Of course, can be scaled down, whatever the other way that we want, so that if they want to test their models using a transmission line, they can use this as their simulated device. And there's a photovoltaic simulator as well, where we can simulate VI characteristics and PV characteristics, so that whatever the this maximum power point tracking and other systems they want to check and simulate, and also look at their various circuit with against their various circuitry they design, they can use this photovoltaic simulator for the simulations. And the bidirectional inverter modules they can use for checking, that standalone operation of grids, and so that as well as hybrid modes where they can operate when the grid fails, how the inverter will work, take over, and then use the photovoltaic energy with or without batteries to supply the loads that are in operation. So in Sri Lanka now, earlier the utilities didn't allow batteries and hybrid inverters, but now they have changed the requirements. Now any house can have batteries and with hybrid inverters. So when the power fails, they can still continue to use the solar PV output together with the batteries if they are sufficient, have the sufficient capacity, and they can enjoy continuity of electric supply. Earlier, even if earlier we had only grid tie inverters, and of course I have in my house still the grid tie inverter, in which case when we have power outages, you can't use the solar PV output even if you have excess power generation, but you can't use them with the grid tie inverter, as we know. But now in Sri Lanka, I don't know about the Indian situation, but in Sri Lanka now they permit you to have batteries, and with proper, of course, protection devices should be there, because when the grid fails, you should not be able to be connected to the grid. Otherwise, you might reverse your power flow may flow to the grid, and then their servicemen will be in trouble. So that is not permitted. So there are various protection devices such as loss of mains and other things, which will protect the solar system to not to feed to the grid when the power is there's a power outage from the grid side, but it will continue to supply the house. Then the lab also has lithium-ion batteries, and so that the students can experiment with them for their usage, because the main grid batteries are operated for the optimality of the system. Our microgrids batteries are programmed to work in certain ways, so you can observe their operating patterns. But with these small battery packs, they can experiment, they can look at various charging, discharging rates, and keep records, and look at how the battery chemistry permits maximum the wattage. And for example, if you want to look at transient situations, how the lithium-ion batteries can be used for quick discharge to maintain the frequency, to avoid frequency collapsing, and to maintain the system stability. And these things they can experiment using these battery packs, which are again available in the lab. And there are grid-connected PV inverters, which will operate only with the grid availability, and which they can use. I think you saw them mounted on the wall, so that the students can plug them to their circuitry and look at how they operate. And this is the meteor station we have. It is housed on the rooftop of the building, so they can measure the ambient temperature, wind speed, global irradiation, humidity, and the air pressure, so that they are input to the main controller. And also the people can look at the trends and history and the trend curves, and how they have been varying over the last so many days. How is the global radiation yesterday, and how is our production, and all these things can be correlated. And of course, they can look at these large data bundles, and they can use this data for various analysis using their this AN techniques and so on. And with this lab, we have set some KPIs. So we want at least 2 PhDs, 2 conference papers per year, and 1 industry-based research and development project, 1 PhD project utilizing the facility from other universities. Every 5 years, at least 2 international journal submissions. Every 5 years, at least 1 new international collaboration. So these are for guidelines. So there's a committee overseeing the operation of this microgrid from university, with the participation of the university as well as Lanka Electricity Company, and from other universities as well. So we have offered this microgrid and the research lab to the use of other engineering faculties of Sri Lanka. So they time to time come here, visit us, and look at the available facilities and spend a day or two, and then get experience on the available facilities and do whatever the experiments they want. So we have a sharing capacity in this lab for the other universities in Sri Lanka. Because some of the engineering faculties are not far away. They are also in Colombo, so they can easily reach us. And we have a business model also in this microgrid, I told you that we can excess energy, we can sell, and for that we can get financially benefited. So in Sri Lanka, there are 3 schemes available for rooftop owners. So I don't know about the Indian situation and your situation. Maybe you have net metering and net accounting. We have 3 systems called, these are our own names, net metering, net accounting, and net plus. I will briefly describe them. In the net metering, you can see that, so this is solar PV, and then the grid coupled inverter, and then you can see the MCB connecting the system, AC to the common bus, and then consumer loads also in the same bus. You can see consumer's main distribution board and the solar PV all connected to the same bus inside the house. And then is the export-import meter of the utility. So it will, during daytime, it might export, during nighttime, it will import, and so on. So at the end of the month, the meter reader will see whether there is a net export or net import. If there's a net import, being the solar production is lower due to whatever the reason, maybe there's a breakdown, or there may be less solar irradiance during that month due to rainy periods and so on. So if there's a net import, so they will issue a bill depending upon the existing block tariff, the present tariff available to that range of housing. And therefore, it will be for that month, it will be a bill. But you might have excess. You might have the exported your production, and mind you, you might have an accumulation of export. If you have an accumulation of export, you don't have to pay. They will not give a bill. They will deduct from that accumulation. That is why we call it net metering. So usually houses have excess generation and zero. They have planned their solar PV system for zero bills. Therefore, gradually they will build up or bank their electricity with the utility. For example, in my roof, I have installed a 5 kilowatt system with a grid tie inverter, and over the last 3 years, until 2000, I think I installed it 2019 also, and I had accumulated about 5,000 kilowatt hours banked at the utility, and they give one-to-one back. I don't know how prudent that is, because they have a cost of their charge. They are taking it up and giving it, but in Sri Lanka it is still one-to-one. I understand that in Australia and so on it is not so. And so it is every kilowatt hour I give to the network, I can take out within 20 years at any time. So then what I did was I bought a Nissan Leaf car and started using it, so charging, and then I started to utilize that banked electricity, 5,000 kilowatt hours. Now it has come down to about 800 kilowatt hours, because my usage by the car during the last 2 years or so. And for last 2 years, I have not paid anything for my travel up and down to the university and close distances, and use my electricity, use my banked electricity. And I make a lot of economic sense. For example, if I run my petrol car, in Sri Lankan sense, it is about, say, altogether about at least 50 rupees per kilometer, 50 Sri Lankan rupees per kilometer, without looking at the investment cost, by looking at the pure fuel cost and the maintenance cost and the tire wastage and so on, without looking at the capital. And if it is 50 rupees per kilometer, and if I use electricity, from every kilowatt hour I use, I can run about 5 kilometers from every kilowatt hour, every unit. So I use 1 kilowatt hour and run 5 kilometers. Thereby avoid 5 into 50 rupees, 250 rupees. So therefore, my electricity I have saved, I'm using to avoid for every kilowatt hour 250 rupees. So in other words, if I can say, I am saying my electricity to myself, me, at 250 rupees a unit. So it makes a lot of economic sense. And within 2.5 years, I have recovered the cost of installing the rooftop system. So it is much better because normally in a rooftop system, if you are going to offset your electricity consumption and recover, it will take 8 to 10 years to recover your capital. But if you use the same with an electric car, so it makes more economic sense. I invite you to look at your circumstances and see whether it makes economic sense for you as well. But you know that an electric car has some limitations, long distance traveling and so on. So of course, it is the second car in our family. So no problem, because if you want to go long distances, we use the petrol car. And all day-to-day small distances, coming to office and going back, etc., we do with the electric car. So in this net metering system, no payments or excess electricity. There's no financial transaction by the utility. So if you produce more and give to them, they bank it with them and then give to you within the 20-year contract period at any time you want. And the second system that we have in Sri Lanka is net accounting. You can see net accounting, the connection is the same, consumer equipment as well as the solar output is connected to the same bus bar. And we have export-import meter the same way. But here the difference is every month, if you have imported more, you have to pay the bill. If you have exported more, the utility will pay you for that. There's no carrying forward anything. Every month you are paid or you pay to the utility, depending upon whether there's a net export or not. So right now, for smaller stations like less than 500 kilowatt, so these are not only for rooftop, also houses only. There are factories and other people, hotels also have connected their roofs to the system. So you can see that is why this 500 kilowatt kind of large number comes. So if the system is less than 500 kilowatt, the utility pays 37 Sri Lankan rupees. That is roughly about, from today's terms, about 11 US cents per kilowatt hour. I think that is a good price. And if it is more than 500 kilowatt, they pay 34 Sri Lankan rupees per unit, which is about 10 US cents. So you can see the prices are good. So, but every month it is settled off. So no carrying forward. So you get an income if you have an excess generation. And the third system is net plus. Here you can see connection is a little different. You have two meters, export meter and import meter. So your solar system is completely an outside power plant. That has nothing to do with your house consumption. You can see that your consumer loads are connected to an import meter and you are charged. You are charged for your imports. And every kilowatt hour you generate from your rooftop is sold out at the same prices that I described earlier. So the advantage is if you are a low consumer, there are block tariffs. You know, if you have 0 to 30 units, maybe 10 rupees a unit, and 20, maybe 30 to 60, maybe 20 rupees a unit. So you get your electricity much cheaper. And then every unit you produce, you sell at 37 rupees. You can see. So it's a big advantage for the small users. So for the small electricity users, so this makes a lot of economic sense, because every kilowatt hour they can sell at higher price and enjoy subsidized electricity for their consumption, for if their usage is small. So this is this was devised especially targeting the poorer sector, and to make a business model for them so that they can get an income. They can get an income by their rooftops. So sometimes one might ask, if they are so poor, how can they install a solar PV system? There's a new business model developed. Now people hire their roofs. There are companies who are hiring roofs of the people and paying them a monthly charge, monthly rental, and then enjoying this facility. So we don't mind, the board doesn't mind because it's a renewable energy development. And if they are willing to invest, so let them do it. And because Ceylon Electricity Board generation cost by fuel is much more than this, we'll be running into 50, 60 rupees a unit. Therefore, every unit generated by solar PV is making economic sense to the utility as well. And that brings to the end of my speech. I planned it, although I was asked to make it 1.5 hours, I make it 1 hour. And I want to play a small video also. To show you the locations and the physical appearance of our lab.
Sorry, sir, for the interruption.
Yes, okay. Yeah, I can hear you.
Sir, you can continue.
Yeah, okay. I will not play the entire video. I will play some sections where technically important for support my talk this morning.
Various forms of power sources or energy sources used in the generation of the...
You can hear and see it. When I played it, can you see the video? And
yes, sir, the video is visual.
Play from the halfway through.
City matter a lot to us, the human beings. The world is about to encounter a huge crisis situation with regard to power and electricity in many ways. Rapid depletion of conventional energy resources, frequent interruptions, and power failures could lead into catastrophic ends in the near future. Inclusion of distributable and renewable energy resources into the networks is becoming a must. Microgrid is an emerging concept which has gained attention in the power industry owing to its contribution to improvements in many ways. Lanka Electricity Company Private Limited, together with the University of Moratuwa, implemented a microgrid pilot project within its franchised area with the aid of Asia's Development Bank. The Lanka Microgrid pilot and the Research and Development Lab are located in the premises of the University of Moratuwa in Kadupatha, Sri Lanka.
Microgrid is an autonomous and self-sufficient energy system. It contains sources like wind, solar, with storage, and load control devices. It helps distribution utilities to increase resilience and power quality, and also to mitigate the issues with high penetration of renewable energy resources. In future, traditional grids will be broken into microgrids during abnormal situations like power transients and loss of power sources. Our microgrid at the University of Moratuwa serves three key focal areas: a solar system, a battery bank, a backup generator, and load control devices have been integrated with a master control device which orchestrates all the components seamlessly. During power outages, it can be worked as an off-grid mode where solar and battery system serves the demand. In case of load shortage, it can shed certain non-essential loads to continuously supply the essential load throughout the time. During prolonged outages, like network maintenance, the backup diesel generator will be coming to the system to have a smooth and continuous power supply. The contract of this project is consortium of VIII and DEMO.
LECO, together with University of Moratuwa, has also established a research and development lab to develop and support research in smart grids in Sri Lanka.
In the past, we produced our electrical engineers to provide cheapest electricity to the entire country. I'm proud to say the success. Today, of course, the emphasis has changed. All our curricula have made environment as a significant factor in engineering. Now we understand that the country needs infrastructure that runs in a more renewable and sustainable way. We hope the Microgrid project will be one of the key initiatives in the island to create more clean renewables into our village. We think this is the way forward for the future. We owe it to the future engineers. We at the University of Moratuwa are happy, grateful to the resistance of regime and Lanka towards this immediate, timely and valuable project to incubate more innovations, cutting-edge technology developments. We welcome all other universities, industries and other sectors, including regional organizations, to join us to build green economy for the generation.
LECO plans to replicate the project in the long run as an extension to traditional distribution network, which catalyzes the absorption of renewable-based distributed generation into the distribution network.
The world is convinced that the electricity generation has a future in the future of transmission is going to be smart. LECO as a distribution entity in Sri Lanka, we are getting increasingly convinced that the future of distribution is going to be microgrids. That is why we consider this particular project is not only a very important project, but the project which determines the future of our company. I'm pretty sure that in the future, our business model as well as our engineering model is going to be microgrids. This is a project where we experiment not only the engineering part of microgrids, but the commercial part of the microgrids as well. How microgrids are going to be a business model for distribution engineering. Therefore, I think the ADB's initiative in granting this project has created a new pivotal point in our roadmap. And I think we have entered into the growth line of distribution.
LECO, together with University of Moratuwa, implemented the Microgrid pilot project with the aid of Asia.
With that, as a concluding words, I would like to say that we are now currently implementing some demand response project together with the microgrid, because we want to optimize the usage when the grid is not available, so that our user generators can be, where operations can be minimized, and also the grid imports when the grid is available can be minimized, so that we are now implementing what we call the new concept, this demand response. So in case the grid is not available, we will have automatic programs to, for example, to not to cut off ACs, but to automatically raise the temperature set point in lecture hall. So if it is set to 25, maybe normal operations, we will raise it to 28, 29, whatever, a higher value, so that the AC load will be reduced, thereby electricity consumption can be reduced. And also we are considering whether some knocking off is also possible, so that the load management is possible. And the demand response, I think utilities in some part of the world, like US, they are utilizing. And I think it's right time that we also look at, in case of crisis time, how to control the devices of the customers, so that the demand can be reduced, thereby making the grid survival possible under even extreme conditions. So, okay, with that, I will once again thank the organizers of STEM 23 and Professor Monalisa, and for inviting me to deliver this talk, and to all the people joined this morning to listen to me. Thank you very much, and I hope I made some technical sense to you and added some knowledge to you, so that someday when you are implementing a microgrid or advanced, you can use some of these.
Thank you, sir. Thank you very much for such a wonderful talk. And really, we are grateful to you for providing us so much of time on this Saturday. Thank you very much, sir.
Thank you. Nice to have met you this.
We sincerely wanted to express our gratitude to you for this informative discussion regarding the microgrid installation and operation in the Sumanadasa building at University of Moratuwa, Sri Lanka. We truly appreciate you and your valuable time for this short-term course. Thank you. Thank you so much, sir.
Thank you, everyone.
Well paid, sir.
Our next session will be taken by Professor Monalisa Patnaik ma'am from NIT Raulkela. It will be started soon.
U is mine. See, I have brought whatever is kept there. You just see C is mixed or not. I don't know, but it is just C also is not the same. That's what. C and